All right, guys, so we're going to get a couple of videos going here on graphing, specifically limacons and roses in the polar coordinate grid. And the first problem in this worksheet asks you to graph these two polar equations that I have up top using a graphing utility. So I already have them graphed, but if you didn't, you should go ahead and give it a try. Just to make sure you know how to graph them, either using your graphing calculator or using Desmos or some other device that you have. In my last video, I showed how to graph in the graphing calculator, and there are plenty of videos out there to help you out with that. And we want to start noticing, hopefully, some patterns with these limacons. Last lesson, we saw a lot of looped limacons, and these are not looped, but they are still limacons based on this graph or this equation setup, r equals a plus or minus b sine theta or cosine theta. So I want you to use this top portion to brainstorm some graphing methods. So if you haven't yet, maybe pause the video and pretend if we were in class, we would be having a discussion. Like, how do we know the highest point that the limacon goes? How do we know that it's up in this top portion of the graph and not down here or over here or over here? Things like that. So think about ways like that. So I would pause me now, and I'm going to write a couple things that I will use in the next examples to help us graph things. So some things that we will use to help graph, one which we've already talked about is definitely symmetry. If you think about our sine and cosine, like especially the circles last time, we know like kind of what sine and cosine values we'll have. I always like to sub in some values for theta, especially the quadrantal angles. And this will come right into play with maybe min and max values, since most sine and cosine graphs, they occur at those quadrantal angles unless, right, the period changes, which we might see. Definitely knowing just like what the parent graph is. If it's a limacon, a rose, a circle, all these things that we're going to start to see. And hopefully you guys have more things on your list, but that's just a start for us. Okay, so last time we talked about symmetry, and here we're going to talk about testing for symmetry. I'm only going to do it on an example or two just to give us the idea. Back in chapter 1, we would check functions for symmetry. Like, for example, we said even functions, f of x equals f of negative x, meaning, and I should really write this like this, right? Like a parabola, we know is an even function. It has even symmetry. So if I put in a negative x, this is the same as our original equation, or could be simplified to the original. So we have similar tests like that for polar grids. But for polar functions, since there are an infinite number of ways to label a point in the coordinate plane, right? Like if I have this point over here, I don't know what the r value is, but let's say this point is 10, and what would this be? 5 pi over 4. Well, I could also call this negative 10 pi over 4, right? I could call it 10, negative 3 pi over 4. So there's an infinite number of ways. So unfortunately, if I'm going to say here, if the equation fails a symmetry test, it may still have symmetry. So it's not like in chapter 1 where if we used a test and it didn't work, there was no symmetry. There might still be symmetry here. So we want to think about point options to test. And we will do an example right here. All right, so going into the equation, you should have kind of a general idea maybe what kind of symmetry the function will have, because here, like cosine, think about our circles. They had symmetry with respect to the polar axis here. So we want to use like a polar axis check for symmetry. So I'm going to do polar axis check. And if you guys remember, the polar axis symmetry was if we had a point up here, like in quadrant 1, r theta, then we would also have a point down here. And we could label this r negative theta. We could label it, I think another way we did was like negative r pi minus theta, right? That's in like the quadrant across. So just like when we put a subbed a negative x in for our even symmetry check, we're going to sub in any of these points. So for this, like I would sub in a negative theta. If I wanted to use this point to check, I would sub in a negative r and a theta minus and a pi minus theta. So I'm going to use this for my check, and I'm just going to compare. So the original equation is r equals 1 minus 2 cosine theta. For the check, I'm going to sub in the changed value, so negative theta. So we'll have r equals 1 minus 2 cosine negative theta. And since cosine is an even function, because we know, hopefully way back from our trig properties, that this is a true statement, then this is the same as original. So that means that this graph has polar axis symmetry. Because if I sub in a negative theta, I'm going to get the same equation. So essentially those outputs will be the same for those, or both work in that equation. So now I'm actually going to graph this. This does have a form of a Limacon, and actually we saw a bunch like this from our last worksheets, a looped Limacon. To graph these, I actually like to first graph it in a regular rectangular plane. This is great review too of graphing these. So I'm going to graph this, y equals 2 cosine x plus 1. I'm just graphing this original equation in the xy plane. So this would be our cosine graph moved up 1, and then a negative 2 amplitude. I'm going to spread this out. So I'll do like every 3 lines is pi over 2. Just do those key values. So cosine usually starts at the max, but our amplitude's negative 2. And I'll show you guys other methods, but I like to use this one because this way I really quickly have 5 nice key points I can use. I'll label them here. Pi over 2, 1. This is pi 3. This is 3 pi over 2, 1. This is 2 pi negative 1. Now remember, it's just the points are switched in the polar grid. So theta comes second, but these are my values. So at 0 degrees or 0 radians, my value is negative 2. So 0 would be here. I'm going to be over at negative 2 on my polar grid. All right. Any point or any graph that has x-intercepts here, so I'm going to say has zeros. So we will have a point on the pole, right? And really what's happening is the radius, right, the r value is just getting smaller and smaller to 0. So this point, as my angle gets bigger, so I started 0, so as my angle gets larger, I'm getting smaller and smaller and closer to 0, and eventually we'll hit that pole point and go through. Then my next point is pi over 2, 1. So that'll be my next point. Going over to pi 3, so 1, 2, 3, and I actually graphed my first negative 1 incorrectly, so I'm going to fix that. Should have been here. Hopefully you guys are yelling at me. Now we're all fixed. So now my next point is pi 3, going out there. What do we have next? 3 pi over 2, 1, and 2 pi negative 1. So back, we would have hit another 0, back to that loop. So this is our looped limacon, and we talked about those last time. So I'm just going to write under here because we'll see other limacons, so we'll compare looped limacon. And this actually happens when in our equation, the A value is less than the B value. All right, the other option for graphing these would just be to try some values, make a little chart, and I would definitely try all your quadrantal angles, right? So when you put a 0 and a cosine, we get 1, so we get our -1. And I already did this with that graph. That's kind of like, I like to just draw it out, so I have 5 points. But even if you do check it with this graph over here, it's still nice to check like another nice value. For example, cosine 2 pi over 3 is a really easy point that works out. So that would be 1 minus 2. Cosine of 2 pi over 3 is -1/2. That's why I chose it. So this would really be 1 plus 1, which is 2. So let's see how far off my graph is here. 2 pi over 3. Yeah, it should be a lot wider, which is fine. I'm only going to check for you guys the points that fall on our like quadrantal angles. So pi over 2, pi, and 3 pi over 2 should definitely be accurate. And then just the shape. So this should be a looped limacon looking like that. But I will clean it up because remember, it has symmetry too. So like once you check this point, you know we're going to have this point. I just checked 2 pi over 3. So I know at 4 pi over 3, I'm going to be out here. So just a little bit fatter. And you guys can check as many points as you like to make these graphs look good. All right, this video is getting pretty long, so I'm going to pause here. We'll have a couple more throughout this worksheet for you guys to check out.